Good day, and welcome to Africa Teen Geek. This is the STEM Digital School. This is a STEM Digital School, and if you have just joined into this classroom, this is the grade 11 Physical Sciences. If you have just joined in, this is the grade 11 Physical Sciences. Today is the 28th of July 2020. My name is Nonkululego Madondo, and I am your Physical Sciences grade 11 teacher. Just getting in there and getting you guys in action and reminding you guys that in this classroom, we work from multiple textbooks, not just one textbook. We have the Siavula textbook, we have the Study and Master textbook, and we also have the Oxford Successful textbook. So you can choose where any CAPS approved textbook that you can use. But it's always good to cross-reference because other chapters are explained better in other textbooks than others. So it always varies. So it's always good if you guys can try and get yourself some good textbook. For example, you can go self and download Snaplify. Snaplify is an application where you guys can get all your textbooks that you need. And on Snaplify, it's absolutely free until the end of the year. So it's not just for physical sciences, for all your other subjects as well. You guys can just go there and get yourself some textbooks for free for the rest of the year. And you can see for English, all your other subjects, guys. So if you do have time, get yourself Snaplify. Okay. I'm also using Snaplify, by the way. And I've got so many textbooks here. Uh, it would seem like I actually live in a library, but no. Okay. So what are we going to do today? Today, we are moving on with electrical power. We're going to first start with our homework that we had to do, and thereafter, we're going to move on to electrical power. As you know, we've been doing the electrical circuits in details for the past few days. We did the Ohm's law, we did applying the Ohm's law, we did the series and parallel circuits, and we also did the combination of both series and parallel circuits. So now we're moving on to electrical power. But just before we do that, if you guys remember properly, we had some homework that was not complete, and we had some homework that was not complete. And I said you guys can go and practice it at home quickly, and then we'll come back today and do some of it as well. So So on 4.1, on question 4, we had a circuit of this. Oh, no, no, no. It's question 5. We already done question 4. On question 5, it says the voltmeter in the circuit in figure 9 reads 15 volts. Okay. So calculate the reading on the voltmeter across the battery. So we've got a voltage here, which is across the battery, which basically once they say that you need to calculate the voltmeter across the battery, it means that you're actually looking for the voltage of the whole entire circuit. Okay. So the battery voltage is the total voltage. So don't be confused there and start wondering what voltage am I going to find in the battery. The battery voltage is the total voltage. Remember why I say this is because the voltage that comes here is the very voltage that goes in here, divides here, and divides it, and then come back as a whole back into the battery. So this is the total battery. Okay. So please make sure you do not get confused there. So the voltage of the battery is the total voltage of the entire circuit. Okay. So moving on. I'm just trying to get into the next page. Okay, here we are. So, oh no. So we're going to have divide our calculations into 3 parts, right? So our first part of the solution is us calculating the voltage through the 75 ohm resistor, which is this one here. First, we're going to calculate the voltage here, and then we're going to calculate, because here the voltage is already given, calculate the reading on the voltmeter. First, we're going to calculate the current in this voltmeter, right? Why are we doing that? Because this series on this series battery, we can actually find the current, and that will be the total current of the whole circuit. So once we have the total current of the whole circuit, then now we can just calculate the sum of the equivalent resistances. And once we have the sum of the equivalent resistances, now we can find the voltage. Okay, so we're going to say voltage is equals to current times resistance, and the resistance in this case, we're going to use the equivalent resistor, the resistance. Okay, I hope we are together. Now let's move on to that. So our first part is to calculate the current. So this current, because it's a series current, it means that it's a, remember what we said, in a series arrangement, the current is equal in all the series arrangement. So I total will be equals to I1, which will also be equals to I2. So that will be the one for the current. So that's why we are looking for the, we're looking for the current on the series branch. Why is that? Because there they've given us the voltage and they've also given us the resistance. So we can find the current there. Okay. So that's how we're going to do it. So first we're going to find the total current, which is also equals to current I1, which is equals to current I2. So the step 2, we're going to select an equation, which is the current is equals to voltage divided by resistance. This is our Ohm's law calculation. We're still part of, remember guys, we are integrating as we move into the electric circuit, and we started with the Ohm's law. We're going to use the Ohm's law until the end of the module. Okay. So it will always be the base of our calculations. So there now, we're going to go and substitute the values, which is going to be current is equals to voltage, which is the 15 volts, divided by the resistance, which is the 75 ohm resistor. So when we simplify that, we're going to get our 0.2 amps of current. So which means that now we've got the current of the whole circuit, because I total in this case is equals to I1, which is I series, which is also equals to the I parallel branch, because once you merge the parallel branch into an equivalent series circuit, it's also going to be in series. So which means that the current that also gets into the parallel branch is 0.2 amps. Okay. So thereafter, now that we have the current of the whole circuit, we can start trying to reduce the resistors in order for us to find the equivalent resistance. How are we going to do that? You know what we do whenever we're looking for the equivalent resistance? The first thing that we do, we first calculate the resistance in the parallel branch. After that, we're going to add it to the series branch and we'll have our equivalent resistance. Okay. So going back to there, we're going to select our equation, which is equals to 1 over R parallel is equals to 1 over R1 plus 1 over R2. And this is the resistance that we found there. Okay, here's our parallel branch, guys. We're going to say 1 over R50 divided by plus 1 over 50 ohms again. So these are both equal, as you can see over here. Okay. So now moving on, now when we simplify it, this is both a common denominator, so it's going to be 2 over 50, and then R parallel, when you swap it around to make it the subject of the formula, you're going to say 50 divided by 2, and our parallel branch is going to give us 25 ohms. Okay, so now that we have our parallel branch and we've got our current, it means that we can find our R equivalent, which is our equivalent resistance, which is the representation of all the resistances calculated into one space. And that is going to give us, calculate the voltage across the parallel branch. So across the parallel branch, when you look for our VP, it's going to be R parallel is times by the current. Okay. So this is what we're going to have as an equation. But you can do it in different ways, guys. You can either look for the equivalent resistance and multiply it with the current, or you can just find the voltages. Like we already have the voltage for the one branch, we can calculate the voltage on the second branch and add them together. So there's many ways to kill the cat when it comes to this. With me, I would have just found the R equivalent and then multiplied it by the current, and then I would have my V total. Okay, but in this case, they did it in a different way. They took the parallel branch and they found the voltage because we already have the voltage on the other side. Okay, so what we have here is going to be R is equals to V over I, and V is equals to I times R, and that's going to be the 0.2 times the 25 ohms. That's going to give us 5 volts. So now that you've got the different voltages, we've got this parallel branch as 5 volts, and we've got this one as 15 volts. So our V total, or our V1, is going to be equals to V series times V parallel, and that's going to be 15 plus 5, and that will be a 20 volt reading on the voltmeter. Okay, I hope that you guys are getting it, and you need to understand, you understanding how we manage to get to these answers. Okay, so now we are moving on. So I hope that you got all these answers correct, and you understand now how to calculate the different parts, either when they're looking for the total voltage, the total current, a voltage in a series branch, a voltage in a parallel branch, current, and all of that, guys. This is very important. I hope that this was very informative, especially this homework question. It came with a lot of tricks that you could use, but like I always tell you guys, there's many ways to skin the cat when it comes to your parallel circuits or your series parallel arrangements. There's many ways that you can do it. Okay, so in this case, they decided to look for the voltage in the parallel branch, add it to the series branch, and look for the potential difference. But others, maybe you can decide that you're gonna get the R parallel, add it to the series branch, and you'll have your equivalent resistance. From there, you just multiply your equivalent resistance with your current, and there you have your answer. So there's many ways to kill the cat. So make sure that you know your different options in finding your answers. Okay. Okay. So now I'm trying to move to the work of the day. Okay. So now we're moving on to power. Okay. I'm just moved too quick and forward. I'm just trying to move back. Ooh, okay. Okay, guys, I'm also reminding you guys that as I move along into this lesson, you guys are free to ask any questions, okay? Any questions that you require, you can just send me a chat and I will try my best to see how I can go back and explain. You don't need to wait until the end of the lesson. Immediately when you get stuck somewhere, raise your hand and ask a question in the chat, okay? So now we're moving to electrical power. As you know, today's lesson, we are dealing with electrical power. We are moving on. So it says here, energy sources like battery transfer energy into electrical circuits. The batteries convert chemical potential energy into electrical energy. Do you see that? There's a conversion because you know batteries, they have chemicals. It's a liquid chemical substance that's inside a battery. So for it to transfer energy into electrical circuit, there needs to be a conversion, okay, from the chemical potential energy into electrical energy. So the energy is used to do work on the electrons in the circuit, okay. So basically, the energy that they talk about is the current flow. The current flow is basically what happens, what needs to happen, and an EMF gets to be induced, okay. So power is a measure of how quickly the energy transfer takes place. Okay, do you guys understand? So power is a measure of how quickly the energy transfer takes place. So energy transfer into electrical circuit, that means the battery is being converted from chemical potential to electrical energy, okay, from one form to another, okay. So there is much larger transfer of energy each second when you use cell phone to make a call than when it's idle. I think you guys can all relate to this example. When your phone is not operational or you do not have a lot of calls that are coming through, the battery lasts longer, right? Because the energy there is being conserved, it's being contained, it's not operating, right? But once you start having a busy phone, for example, when you use too much WhatsApp and your internet is moving too fast and you have too many calls, then all of a sudden your battery starts depleting very quickly. That's because the energy transfer in each second is much more. So the too much power that your phone is using. So that's a typical example that you guys can get. Okay. So they say in electricity, power is the rate at which electrical energy is converted to other forms of energy in an electric circuit. Okay. So this is the rate at which electrical energy is converted to other forms of energy in an electric circuit. Guys, please make sure that in every section you get to understand what the power meaning is there, because you know power has so many meanings. In each and every chapter we have power, but it's got a different meaning in it. Okay, so in electricity, like they specify here, in electricity, power is the rate at which electrical energy is converted to other forms of energy in an electric circuit. So power is a scalar quantity and it's measured in watt. 1 watt is a transfer of 1 joule of energy per second. Okay, so that's another thing that you guys must also bear in mind. As much as power has different meanings in different parts of the physics, in physics, but it all has to do with time. Okay, so it always has to do, because anything that has rate already has time. It's already divided by time. So that's what power is. So as you can see here, I've got some equations which says power is equal to energy transferred divided by time. So these are our symbols. So energy transferred, it means that is the change in energy divided by the change in time. So P is in watts. Triangle energy is energy transfer or converted into different forms, and that is in joules. And therefore, we have our triangle T, which is the time taken. Okay, so our time taken is most important. So the power rating, now we come to another definition, which is the power rating. The power rating is the rate at which the device transforms energy. Power ratings are indicated in watts or kilowatts. The table shows some typical values of domestic appliances. These are the average values and they vary according to the model. For example, guys, you can see in all your electrical appliances inside the house, wherever, if for example, you buy a hair dryer, you can see on the hair dryer or on the box, there's a certain rating that's written. For example, it will say 1,500 watts, etc. It has all those ratings. These are the average values that, and they vary according to the models. Okay, so power rating is the rate at which the device transforms energy. So basically, it's the amount of power that is the maximum amount of power that your device can use or can transform your energy. Okay, so the higher the rating, which means the more the faster or the higher the performance of that electrical device. Okay, so those are some of the things that you should also know. So geysers and washing machines and fridges, for instance, they all vary in using amounts of power at different times. None of them use a constant amount of power all the time. Why is that? Because, for example, a geyser, people are not always bathing. So when you bath, that's when your power is operational and you're using a lot of power. But as time goes, maybe during the day there's nobody bathing, it go back to zero. So it's not a constant fixed amount of power that is used at all times in this case. So you also have washing machine. Washing machine, sometimes your load is heavy, sometimes it's light, sometimes it's medium. So it's not constant because you do not use the same amount, but you'll have a rating of the maximum amount that of power that can be used at a time. Okay. And a fridge as well. Remember, fridges, they also have ratings, and they also have the switches where you can change whether you want it to go number 4, number 5, or number 6. That is a changing value. So it's not constant as well. But you will always have a maximum amount of power rating that you can use for that specific machine. Okay. So now we're moving. Energy converted in joules is equals to power in what? Times time. Okay. So this is our little triangle. As you can see, remember, we had our power is equals to energy divided by time. But energy in this case is equals to power times time. So we have a lot of triangles in physics. So you must always make sure that you have all your triangles ready because they really help a lot, especially when you try to manipulate your formula to look for something else. You need your triangle for this. So you can also have a triangle for power in this case. So the energy converted when a charge moves through a potential difference V is VQ. Then the power is equals to energy converted divided by time. So what they say here is that electric current, which is I, is the charge that flows per second. Okay, is the charge that flows per second. So P is equals to VI. You guys remember where we found this from, right? This is our also part of our this is also part of our Ohm's law. Okay, so this equation gives us the power converted by any device. So this is the equation which is Q over time. So P is equals to V times I. So this equation gives us the power converted by any device. When I is the current that passes through it, and V is the potential difference across it. Okay. So remember, I is always in series, so that's why it passes through it. But when you calculate the voltage, it's the potential difference across it. Okay. So the rate of energy conversion in a resistor R can be written by substituting the Ohm's law, which is equals to V is equals to IR into the I or the V in the equation of power. So you remember we once did the triangle for the power equation, and we mentioned how it changes when you can either substitute one of the two, one of the three actually. You can either substitute voltage or you can either substitute the current, but either one of them, it will give you something similar to this. So P is equals to VI. If we take the Ohm's law, which is V times R, and we substitute the voltage, it's gonna be I times R, and that's gonna give us I squared R. Okay, so that's how we calculate the power. And for if we decide to, but guys, I want you guys to remember one thing, yeah? What we substitute our power there, which formula we choose to use to replace the Ohm's law depends on what is given. If they're asking you for power and they've only given you current and resistance, then you know that you're going to have to substitute the V part so that you do not have to look for V substituted there, and you can have I squared R according to what you are given. If, for example, in your problem, you're asked a question and what they've given you the voltage and they've given you the resistance. It means that in this case, our Ohm's law, we're going to replace it into the current equation so that you have V squared over R. So it's always important to note that it always depends on what is given as to what you substitute. So these are our three formulas for power. Power is equals to V times I, or if you are given your voltage and your current, you will say P is equals to V times I. But if you are given current and resistance, then your equation will be P is equals to I squared times R. But if you are only given your voltage or your resistance, then this is the equation that you will use. Okay, So any of these equations for power can be used to solve problems. It depends on the quantity known and asked as to which equation you use. So this is shown in the following example. So now we're going to have a couple of examples that we're going to do, and we're also going to go to textbook questions as well that we're also going to refer to, just to make sure that we do our dry run on the power equations. Okay, so it says here, we've got example 1. It says calculate the current. So they say that a power station produces 20 megawatts of power at a voltage of 200 kilovolts. Okay, what current does it supply to the grid? Okay, so now we come back and we look at what we have. We need to write down everything that you have. You have to write the first line, what is given. What is given here is the power. They've already given you power. They say power is 20 megawatts of a voltage of 200 kilovolts. So how are we going to solve this problem? We're going to check what is given. We have power and we've got voltage, and what we are looking for current. So we're going to go back to our little triangle equation. We're going to go back to our triangle equation and we're going to see. Remember, we've got 3 equations of power. The first one is P is equals to VI. The other one is P is equals to I squared R. And the other one is P is equals to V squared divided by R. But this one looks like the one that is more suited for this equation because we are looking for the current, we've been given power, and we are given voltage. So rearranging this equation for us to make I the subject of the formula, it's going to be P over V. And don't forget, guys, if this is megawatt, is times 10 to the power of 6. And if this one is kilo, it means that it's times 10 to the power of 3. So make sure that you add them there, guys. Don't assume that this is the standard formula. No, this is our power is equals to watt. So if we have an M, it means that it's megawatt. If it's kV, it means that it's kilovolt. So it's times 10 to the power of 3. And there you will have yourself your 100 amps of current. Okay. Then let's move on to the next one. Example 2 says the current from the station flows through power lines 15 kilometers long, right? With a resistance per unit length of 0.2 kilometers. How much power is wasted in this line? Okay. So what are we going to do? The first thing we're going to do, we must calculate the resistance of these lines, right? So what do we have here? We've got the kilometers and we've got 0.2 kilometers minus 1, right? So for us to know the resistance, we need to say the power line times the resistance per unit length, and that will give us the amount of resistance because the kilometers are going to cancel each other out, right? So this one is 0.2 ohms per kilometer. So which means this kilometers is on your denominator. So if you going to say the 15 kilometers times by this, the kilometer is going to cancel out, and what you're going to have left is your ohms, just like you have it here. So resistance is equals to 15 kilometers times 0.2 ohms per kilometers, and that will give you 3 ohms. Okay, so which means that what do we have now? We've got our resistance. Okay, so now as we are given current and resistance and we want to find P, it means that we can find our I squared R. Remember, guys, this question is continuing from the one that we just found here, which was the 100 amps, right? So we've got our current and now we've got our resistance, which means that this equation is the most appropriate equation for us to use. So our power is going to be equals to current squared times R, and that's going to be 100 squared times 3, and that will give us 30 kilowatts. You see, sometimes you need to simplify it further. If you can't just write 30,000 watts. You can have it as 30 kilowatts, okay? And that will be your simplified equation. Okay. So now I want us to quickly go to our textbook on our Siyavula. If you have it, but you can also read through because I'll be also opening it on my side. Okay. I just want us to do a couple of examples there. So we've already passed this stage of deriving the equations. So here is also another example. They say here, given a circuit component that has a voltage of 5 volts and a resistance of 2 ohms, what is the power dissipated? So what are we going to use here? Here we've got the voltage and we've got the resistance. It means that for power, we're going to use this equation here that says V squared over R. Okay, like I always tell you guys, the equation that we choose is always determined by what is given. Okay, so first you write down what you are given. Like I always tell you guys, make sure whatever you do, you write what is given. So you've got your voltage, you've got your resistance, and you've got your power that you need to find. So power is equals to V squared over R, right? And that will give us 12 volts. Okay, so this one is a bit simple, right? I'm sure that everybody can be able to solve that. So let's go to the next question. The next question says, study the diagram below. The resistance of the resistor is 15 ohms and the current going through the resistor is 4 amps. So what is the power of the resistor? So first of all, you know what to do. We need to find out what is given. And what is given in this case, we are given the resistance and we are given the current. And so which means that we're going to use the equation that says power is equals to I squared times R. And our I squared in this case is going to be 4 squared times 15 ohms. Okay. And there we have it. So it's going to be 240 watt. Okay. Guys, I hope that this makes sense to you guys. If you are getting stuck somewhere and there's something that you're not sure about, please let me know so that I can quickly go back and explain it to you. Okay. Do not get stuck alone. This is a classroom where you get to learn. Understanding is the most important part of this classroom. Okay. So on this question, it says 2 ohmic resistors R1 and R2 are connected in series with a cell. Find the resistance and power of R2. Okay. Given that the current flows through, oh, that's great. Given that the current flowing through R1 and R2 is 0.25 amps, and that of the voltage across the cell is 6 volts. So our R1 here is 1 ohm, and we don't know what is our R2. Okay. So now we need to find what we have. Okay, first what you do first, you draw your circuit, okay, so that you can be able to see what you have. And we know here we've got our voltage across the whole cell, right? So this is our V total and this is our I total. So what do we know about current in a series resistance arrangement? We know that the current is the same in both resistors because they are in series. So the I total is equals to I1 is equals to I2, right? And we know that our voltage is dividing there, okay? So they want us to find the resistance and power of R2, but it's not going to be so difficult to find it, right? Because what we can do here, if we've got the current there, we can find the voltage of R1. And what are we going to do there? We're going to say V1 is equals to I total, which is the same in the whole branch, times the R1, okay? And then we're going to find the voltage for this one. And once we find the voltage for this one, we can use the equation of V total is equals to V1 plus V2, and we make V2 the subject of the formula, okay? And then now we'll find V2. Once we have V2, we can find R2, which is going to be R2 is equals to V divided by I. So let's just see how they did it here. Like I told you guys, there's many ways to kill the cat when it comes to these equations. Maybe the one that I've just explained to you now is not the one that is used, but there is many ways to kill the cat when you are working with your Ohm's law and your electrical circuits, okay? So now they say the first step here, we need to determine how to approach the problem. So we can use the Ohm's law to find the total resistance. So you see, in this case, what they did, they used the Ohm's law to find the total resistance in the circuit and then calculate the unknown resistance using R is equals to R1 plus R2. But you saw how I did it. What I did, I first calculated the voltage and tried to find the V2, right? And from V2, then I went straight to the equation and said R is equals to V2 divided by R2 is equals to V2 divided by I2. But in this case, they want to find the resistance where they're going to say R is equals to R1 plus R2. And because it's a series. So what they did now is they tried to find the total resistance. And the total resistance in this case is going to be voltage divided by current. And the voltage divided by current is going to be 6 divided by 0.25. And that's going to give us 24 ohms. Okay. So you see how this method is being done. I hope that it makes sense and you are understanding. Okay. So now that we found the resistance of the whole circuit, and we also have the resistance for R1, now we can find R2, because we can say R is equal to R1 plus R2. R2 is going to be R minus R1, and that's going to give us 23 ohms. So now we have solved the problem for the ohm. So now number 2, they said we need to find the power for that resistance for R2. Okay. So what we're gonna use the equation of I squared times R. Why? Because we're checking what is given. We didn't have to calculate the voltage for this part. So we have the current and we have the resistance that we've just calculated. So which means that our power is going to be current squared times R. And the R is going to be the one that we've calculated, and the I is the same in the whole circuit. So it's still going to be 0.25 squared, and that's going to be 1,44 watts. Okay. Are we together? Okay. Let's just see. And so you will write your answer that the power for resistor R2 is 1.44 watt. Okay. Oh, I'm loving these problems, guys, because they are so much and there's so many for us to choose from. We're going to have nice homework for us to do. So here's another interesting one. Remember, we did our series parallel circuits. So here is another problem that is like that, a power problem. Because guys, you guys need to remember that when you get to your test on exams, they can ask you all of these questions using one circuit. So they're not always going to say, okay, now let's move to the chapter of power. No, they're not going to do that. They're just going to give you a circuit and they're going to ask you all the problems from calculating the equivalent resistance, calculating the resistor in one of the parallel branches, calculating the power, calculating the voltage. They're going to make it one problem. Okay. So you need to make sure that you know how to solve it. So now we've got this circuit, right? We've got two parallel branches. We've got R1 and R2, R3 and R4. So these ones are paired together. What we know, when we're going to try and solve this, we're going to have to first do the parallel branch for this one, and then we're going to calculate the parallel branch for parallel branch 2, and then we're going to add them together. Because once you calculate these two, it's going to be a single unit, and this is going to be a single unit, and they're going to be in series together, and you're going to have to add them to find your equivalent resistance. Okay. So now they say the current leaving the battery is 1.07 amps. So which means that the current that is flowing here, it's 1.07 amps. It comes here and it splits between these two, and it comes back again, and it becomes 1.07 again. It comes here and it splits again, and it comes and joins back here again. And the current here again will also be 1.07 amps, and it's going to go in and it's going to keep rotating in that manner. So the total power dissipated in the circuit is 6.42 watts. So here they've given us the power. Okay. So they say the ratio of total resistance of the two parallel branch network is 1:2, and the ratio of R1 and R2 is 3:5, and R3 is 7 ohms. Okay. So which means that if for example R parallel is equals to 2 ohms, it means that R parallel branch 2 is going to be 4 ohms, because they said the ratio is 1:2. Okay. So what they've given us here, they've given us the R3. So what can we find from R3 alone? From R3 alone, we can actually find the voltage. Okay. So okay, we don't have enough time left, guys. I was just getting carried away with the time. But what I think that we can do this tomorrow again, okay? We'll continue with this problem. But I want you guys to go and do it as homework. Okay. Can you guys take this problem as homework for tomorrow? And then we can see if you guys can solve it. We'll start with it tomorrow before going to other problems, because we still have a lot of problems that we haven't done for the series parallel circuit that we still need to do. Okay. That we still need to do for power dissipated. So can you just take a screen grab of this and try and attempt it at home? Okay. So number one, these are the questions that we need to solve. Let me just make this a little smaller. Yeah. So it's a little smaller. Let me just hide the solution. So you're going to have your problem like this. This is your circuit, and you've got all of this. So they're going to, the first question is calculate the voltage of the battery, right? Calculate the voltage of the battery, which means they want the total voltage. Remember, I told you, whenever they say the terminal voltage or the voltage in the battery or the voltage in the from the source, they're talking about the total voltage of the whole circuit. So this is what they want here. They want VT, V total. And number two says the power dissipated in RP1 and RP2. Okay, so which means that now we're going to have to work with the individual parallel branches and find the power that is dissipated. Okay. And then number three says the value of each resistor and the power dissipated in each of them. So this is a very long question, guys, but I know I trust that you guys will be able to do it. It's good for homework. And tomorrow we're going to continue with some more problems of power, and hopefully we'll still gonna have enough time for us to we will still have enough time for us to do the rest. Okay, to do the next part of the power dissipated. Guys, thank you guys so much for a beautiful class. My name is Nonkululeko Matondo, and if you are in this class, you are here for Physical Sciences grade 11. And I just want to say our time is up. And please, guys, do not forget to do your homework. Please do your homework, and please do your homework. And please, guys, just remember the concepts that we use. They are all the same. They just placed in different ways and different things that you look for. But for me, Nonkululeko Matondo, we have reached the end of the class. And thank you guys so much, and goodbye.